Hello, my name is Surya and this is Lab 4, Circuits. So the purpose of this lab was to predict the behavior of circuits with resistors in both parallel and series. We will do this by observing the loop rule and conservation of energy. We will look at charging and discharging a capacitor, and we will examine how close actual values of a conventional current and potential voltage difference are to theoretically calculated values. So some fundamentals: charge conservation and energy conservation in circuits, and we will look at RC circuits, specifically time-dependent voltage across a discharging capacitor. So the first circuit we had to make was this DC circuit. So from Ohm's law, we can see that I should have been equal to 0.0204 amps, and in fact it was equal to 0.02 amps. And when I switched the ammeter the other way, it was equal to 0.02 amps again, because I believe the model takes absolute value in the ammeter. So next we had to replace one of the ammeters with a voltmeter. So this voltmeter read 3 volts because of the total of the two batteries, and then the ammeter shows 0 amps because the circuit is essentially open because the voltmeter has such a high resistance. So we were asked to take readings of potential differences across certain points. So as you can see, here's the potential differences between all the points, and what we're kind of trying to see is that the sum of all of these is equal to 0 volts, which was actually true, and this confirms the loop rule. So now looking at the graph of our voltage drops, so first from A to B, because of the two batteries, it jumps to 1.5 volts and then jumps all the way to 3 volts, and then from B to C it stays constant. From C to D it drops by a little less than 1, and then from D to E it stays constant, and then from E to F it drops a little bit more than 2, and from F through H it stays constant at 0. So other questions on part 1. So when you attach a voltmeter, you alter the circuit. Why doesn't the ammeter reading change? So the ammeter's reading is actually dependent on voltage and resistance, and through Ohm's law, and both these values are unchanged. So now connect the voltmeter across a 100 ohm resistor and note the reading. So this was 0.02 amps. Now we replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. So we're trying to look at what happens to the current through the other ammeter. So now the reading is at 0.06 amps. So this is because the current takes a path of least resistance. So now calculating the resistance at certain points. So at the R47 resistor, it's equal to 47.95, and at the R100 resistor, I got that it's equal to 150 ohms, and at R wire and R ammeter, these are both 0 ohms. So now onto the RC circuits. On the left, we see a capacitor being charged by a battery going through a light bulb, and on the right, we see a light bulb that is being charged by the capacitor. And in these two models, the charge is actually moving in the opposite direction. So the current in the circuit actually decreases as the capacitor is charged, and when we remove the battery from the circuit, the charge in the capacitor went to the light bulb, so the current actually jumped to around its original level and discharged again slowly. So the discharging and charging times are, as you can see, like 10 seconds for the 10 ohm light bulb and about 20 seconds for the 20 ohm light bulb. So the final circuit graph is a graph of the natural log of V over V initial versus the time. So this is a negative sloping graph, and we're trying to find RC, and the slope of our graph is -1 over RC, so we get RC to be equal to 6.006 seconds, and the theoretical value is 6 seconds. So it makes sense that these values are close because we're using a modeling software that was based on code. So now, what if we were doing this lab in real life and used the actual ammeter? So the amp readings would be lower because there would be more resistance in real life. And what if we were doing this lab in real life and used a real battery and a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this happen in real life? So our ideal model would predict that the capacitor would instantly reach full charge with no resistor. This would not happen in real life as the wires themselves do have some resistance. It would be very interesting to see how these values would actually be if we used a real circuit with less than ideal situations. So thank you for listening to my lab.